Hi guys, Mr. Ford here again. We're going to continue with worksheet 4A, then move on to worksheet 5. So hopefully remember a little bit about plane mirrors and reflection, that light will bounce off a flat surface at the same angle that it comes in as it leaves at. So we talked about the incident or incoming light ray having an angle of incidence, which would be equal to the angle of reflection, or that bounced off reflected ray. So if you're watching this video right now and you haven't completed the ed puzzle for today on refraction of light, or you haven't completed the Schoology quiz on reflection, please stop and hit pause and go back and do those two things first. All right, so here we have a mirror and an object. It's just an arrow, just a drawing with a little dot. Something to note here is that the mirror is at an angle to our image. So we're going to be looking at tracing the light rays. So the easiest thing to do, and then part B, we're going to position an eye where we could see this. So the thing to keep in mind is that if you remember back from force diagrams, what we did if things were angled, we tilted our piece of paper. So that's what I think you should do right now, is just tilt your piece of paper so that that plane mirror is either perfectly horizontal or vertical. Mine is just horizontal. And what we remember from last time is that whatever this distance is, this perpendicular distance from the object to the mirror, is the same as the image distance. So if this was, say, like 2 inches in front of the mirror, our image would be 2 inches behind. So we're going to use that idea, that concept. And that's what we're going to continue to do with mirrors, or flat mirrors, since we don't possibly have measurement tools or protractors at home. If you do have a ruler, that's great. If not, use some kind of rudimentary way of keeping the same distance, using, like, different joints in your fingers, markings on a pencil or a piece of paper work fine. So what I'm going to do first is draw on our normal line. Our normal line is our line that is perpendicular to our surface. So our image is going to be someplace along that line. So again, if we are about, I'm going to use my ruler here, my piece of paper, or actually, not paper, it's about 2 centimeters in front of the mirror. So my image is going to be about 2 centimeters behind the mirror. That's pretty easy, right? Same thing we're going to do for our tip of our arrow. And the reason why we're picking the boundaries is because if we can track the light rays of these two parts of our image, or I'm sorry, object, all the ones in between, we would be able to see as well, because there's going to be an infinite number of light rays. So if the tip of my arrow here is about 3 centimeters in front, about 3 centimeters behind, I'm going to see the tip of my arrow right here. So I'm just going to roughly draw my arrow. And that's what I'm going to see in the mirror. Okay. Easy. Hard part. Tracing the light rays. So I'm just going to pick a random location. Go right here. Here's my eyeball. And if you remember from last time, this is kind of like the side view of an eye. Okay. So remember, our brain thinks light travels in straight lines. So if I'm going to look at the circle part of my arrow, my brain is going to think that the light comes right from that source. So my brain is thinking this. You might not want to draw this yet, because that's what my brain thinks. But the light's not really coming from behind the mirror. So I'm going to make that a dotted line, because dotted lines on ray diagrams show where the light appears to, or the virtual image. So where that light is actually coming from, it's coming from our image, our actual dot. So it's actually coming out here, bouncing off of here, and going to our eyeball. So that's one way to draw that light ray. And keeping in mind that this angle here and this angle here are equal to each other. And if we really wanted to go inside, these angles are also equal. They're the true angles of incidence and reflections. So that's one way. The other way is, and it was mere coincidence that this was at that line there. The other way to trace the light rays, so if that was the light rays for that part, I'm going to go red for the ones of the tip of the arrow here. We know that since the light is going to bounce off on equal angles of each side, if we measured this distance from the eyeball to where the horizontal distance to this point would be, right in the middle of that, so I'm just going to estimate the middle. Pretty good. That's where my intersection would be, meaning that's where my boundary of where the light's going to bounce off of. So what I could do is draw a line. So the light's going to come off the tip of that, hit that point on the mirror, bounce off at an equal angle. And you can see just kind of visually, it's not perfect, but this side and this side are pretty close. If we had a protractor, we could show that they were off by less than probably 2 degrees. My normal line is not necessarily the best right here in showing between those two, but that's fine. And the light's coming this way and then back into the eye. So that's another way. Instead of tracing it to the object like we did the first time with the blue line, we can split that difference, that horizontal distance between our object and our eyeball. And to test it, this should match up pretty much. If we extend the line that, if you imagine like the red light coming out of your eyeball, if we extend that line back, that's the direction that our brain is perceiving the light come from. Just like with the other one, our brain was perceiving the light come from this way. These are the directions that our brain is perceiving the light from behind the mirror. But the light is actually coming from in front, bouncing off, going to our eye in both scenarios. And now to my favorite part, Mr. Eyefoot. You can see why we call Mr. Eyefoot. He's a foot and an eye. So this one's a little bit easier since we have everything is just horizontal. So we know whatever this distance is and this distance, our image is going to be the same behind the mirror. So if you have a ruler, feel free to do that. I have to this straight line, it's about 3.5 centimeters. So that's my 3.5 centimeter mark. So I'm going to do my best to draw a vertical line here. That's about the best I can do. Extend that this way. Cool. So again, I'm going to estimate where the top of his hat is, or I'm not estimating, I'm actually drawing. So right there. So this is the top of his hat. Kind of funky hat. Here's his eye. His foot. Kind of weird. Good enough. Let's see why I did not pursue art. So, one way, like we mentioned before, if you want to look at your hat in the mirror, you will look at the image of the hat. So this is the part where it kind of makes sense to imagine laser beams coming out of your eyeballs. So if we had a laser beam come out of our eye and we need to make a straight line to the top of the hat, that's the direction we would look, right? But keeping in mind that that doesn't really happen, and to the right side of our mirror, it is a dashed line because that is not real light. Where that light is actually coming from is the top of the hat. She can't get it on here. Good enough. Bouncing off of the mirror and then going back to his eye. But it appears that it's coming from the hat. Same thing with the foot. Right, what we could do is measure a different distance from his eye to his foot. Find the midpoint of that, right? And I'm just estimating here. And that's where that intersection would be of the light coming off his foot and then going into his eye. The only thing with that is you have to have a measurement tool. So without a measurement tool and kind of being difficult to measure on an iPad, I'm going to go the other method. You'll see that it should match up pretty close. So again, if I want to look at my foot, I look at my foot in the mirror, and keeping in mind that that's not real light, but we think the light's coming from there into our eye, but what it's actually doing is coming from our foot and bouncing off. So we see our path of our two lights to see our hat and to see our foot. Oops. And the size of mirror that we would need would be this size mirror. So you don't need to actually have a full-length mirror to see your whole body. We'll get to the size in a minute. This one actually does say, compared to your height. So what we could do is if you measure that height relatively or with a ruler, what you'll find is that the size of this mirror, this kind of like a salmon color, is exactly or pretty close to half of Mr. Ifoot's height. Which if you think about it, what we did here was we split this distance in half, right? That's like the distance from his eye to his head. Split that in half. That was the intersection point here. We took the distance from his eye to his foot, split that in half. So essentially we're taking his whole height and splitting it in half, and that's the size of the mirror that we need. Well, what about if he backs up? You can see that we have a further distance. We can go through the same methods. I'm going to go through a little bit faster here. So the first part's going to be slow because I have to measure. So now he's about, 7.5 or so. Could be a little bit faster here. So he's about here. Here. So this is like the top of his hat. His eyeball. His foot. Get rid of that random one. Okay. So again, if we want to look at the top of the hat in the mirror, we look there. But again, that's not his real image. The light is not actually coming from behind the mirror. We just kind of do that as a little trick to see where on the mirror the light's hitting, because it's actually coming from the top of his hat and then going into his eye. It keeps the color. Once I look at his foot, looks at his foot. So the light's going this way. It's actually going to bounce off of the mirror here. Oh, what was my mistake? One mistake. Let's see if you picked this one up. Yeah, the first mistake is I didn't go through, make that dotted line. But light does not come out of your eyeballs, Maddie. So making sure that the light is coming from the foot, bouncing off the mirror, and then going into the eye. And then we have, yet again, this is the size of the mirror he would need. Interesting. You would think it would have been either smaller or bigger. So this is another trick that our mind plays on us, that if you back up from it, so if you go real close, if you have a full-length mirror in your house someplace, or you go real close in the bathroom, and you could see a certain amount of your body. If you back up, usually you could see more. But what we're not thinking of is our eye is tracking up and down. So you're looking at the top of your head, and then you're looking at your feet. And that small amount of movement you're not perceiving. of your eyeball moving up and down. In this ray diagram, we're assuming that we're always looking at a certain, we're not really shifting it up or down. So if you look and you measured this distance here in the salmon color again, it is the same size as before. It's still half of his height. And you look at the triangles in both 8 and 9, you'll see it's really just how the light is moving relative to, or the sizes of those triangles are still getting bigger and smaller, but the angles are really staying the same. All right, so hopefully that made sense. And you're going to continue on to the next video for worksheet